We had 12 minutes to do it, so we ended at 2:12. We can start it at 2 and still have time to finish it.
Okay.
That makes sense. It would take like 5 minutes.
Yeah, it doesn't take me that long to do this.
Yeah.
I did the first A and 1A and 1B.
Almost on 1A.
It took a while, but 1B is easier because it's the same thing as 1A. So once you get 1A, you're fine. Did you finish right now? I was gonna look at it. I mean, no promises. I mean, also. I can't find my erasers. It's gone missing for like a day. A lot of mistakes, so.
Have you been writing down the? That's good for P. We missed one. Oh, I guess not. Talk about it later. I think it's due Tuesday.
Yeah.
Really should have a midterm.
Okay. Any questions before we start? Online, in class?
How long does your review go for today?
Would you what?
How long does your review go for today?
Till one of us drop. Normally, it's when questions and first review session, I think 2 students showed up and we went for like half an hour. Second review session, I never did. This review session, if people have been keeping up with the homeworks, there may be a lot of questions. And, you know, it can be on any question in the course, but typically the focus is the problems on the syllabus I do not collect. So if we're going until 6 o'clock, we're going until 6 o'clock. Okay, so we've been working with energy. And again, what we recognize that along a path line, this sum of these 3 terms, velocity head, pressure head, and elevation, is a constant. We call that constant the Bernoulli sum. And we can just call that a capital B. So again, along that path line, we can say that total B is equal anywhere. And what may be changing from point to point to point is any one of those 3 terms. We cannot have different fluids, different gammas, because then you would not have a continuum. That was one of the fundamental assumptions that we had. So you could have one fluid moving over another, and you can apply energy in each fluid individually, but you can't draw a path line from one into the other. It's actually pretty important, especially when you're talking about systems in which you have flows occurring due to density differences. For example, fresh water and seawater, or a pollutant. For those of you environmentalists who take fate and transport, you may actually have a separate phase fluid, or you could have just a denser phase fluid on the system compared to fresh water. And those two will be subscribing to energy considerations, but in their own phases. And then we talked about the fact that those 3 terms sum to what we call the energy grade line. And so if you can draw the path line, and along the path line, you can calculate the Bernoulli sum B anywhere, you can plot out B everywhere for that path line, and that's known as the energy grade line. Right now in systems, without energy losses, no viscosity, and without mechanical energy, that energy grade line is just a horizontal line, or if you're talking about a system, it's a horizontal surface over the system. In the future, that will not be true. Once we get energy losses, once we have mechanical energy, then the energy grade line can move around. And the hydraulic grade line is the sums of the potential energy, and that would be P over gamma plus Z. So for example, if we just looked at the center line of the pipe and called that our elevation, the distance between that center line of the pipe and the hydraulic grade line is just P over gamma. HGL is P over gamma plus Z. And any one of those values could be zero. All three of those values could be zero. The energy grade line could be a positive number, could be a negative number, but it's a real number. So typically when we're looking along the path line, what we'll do is set the total energy at one place equal to the total energy at another place. B1 is equal to B2. And what we did last time was I reviewed how we solved the problems. I gave you all this information before. The last two lectures we had these. We talked about where we select points. Normally you select points where you either want to know something or where you already know something, because that helps you determine some of the variables in that equation. And then last time what we did was just apply this without any numbers first to a very simple problem, the leakage from a tank. And in this case, what we said was we selected 0.1 at the free surface because we know a lot of information there. We also, following the guidance I gave to you, set our elevation datum right at the center line of the jet. And so what that allows us to do was cancel out a lot of terms. And we basically had that the total energy on one side is just H, and the total energy on the other side was the velocity head of the free jet. Pretty simple. And again, that happened because of where we took those 2 points. And so again, what that then reduced to, so we started off with the equation I just had up there. We came up with the Torricelli equation. And again, if we were after the discharge, that would just be that velocity we found times the area of the orifice. And again, this seems like a pretty underwhelming answer, but this equation, it's either called the Torricelli equation or more commonly the orifice equation, because flow is issuing out of an orifice. It's used for so many actual real problems. Last time I talked about leakage from pipes, but I also talked about how you actually use water. We store the water basically as potential energy, either H or P over gamma. And at the very end, where you turn the valve, we convert it all to V squared over 2J. So this is actually a fairly important equation when we're talking about moving fluids around, especially in pressurized systems. So I wanted to do an example today. And to help everybody keep up with me, I didn't prepare any slides for it. So the system is going to look like this. We're going to have a pipe, and it's going to expand. So it looks something like this. And flow is moving upwards and to the right through this pipe. And what we would have is a diameter down here of 15 inches. And the diameter up above is 24 inches. So let's call that D1 and D2. And so obviously this is an expansion. And we're going to have a pressure gauge in the smaller diameter pipe down here. And that pressure gauge is giving us a reading of 60 pounds per square inch. And we know in this case, the center line elevation of the pipe is 108 feet, for example, mean sea level. So when you see something like that, feet mean sea level, it means you're referencing it to a national geodetic vertical datum. And so everybody in this country knows what that is and can associate their elevation to that. In the last problem we had with the Torricelli, what we did was just arbitrarily set a local elevation datum. Just like on the surface, we have a local pressure datum, and that's atmospheric pressure, and that's 0 up there. So with these linear scales, whether it be elevation or pressure, the important thing is typically the difference from one location to another, not necessarily the absolute value. Again, if we have 20 feet of elevation difference between the floor and the ceiling in this room, if we call the local floor elevation 0 and the ceiling elevation 20 feet difference. If we measure this real elevation to be 210.21 feet, that would be 231.10 feet. Still 20-foot difference, but now reference to, say, the National Geodetic Vertical Datum. So just be aware of that. And in this problem, where I show the pressure gauge giving us 20 PSI, for your homework problems, or heaven forbid on an exam, that could be a manometer. And the manometer is telling you nothing different than what a pressure gauge is. It's telling you pressure at that location. So in this case, we're going to have a known discharge. And so our discharge is going to be 14 cubic foot per second. And the fluid in this case is oil. And in this case, the specific gravity of oil is 0.83. And you know that the specific weight of oil would be the specific gravity of oil times the specific weight of water. So we'll be using that later. So given all of this information, at this location, we're going to say we have an elevation of 128 feet. Also with reference to the same data, mean sea level. And for all this information, what we would like to do is compute the pressure at the second location. So we're going to call this first location 0.1 and the second location 0.2. Why did we pick 0.1 where it is? Because we know information there. We know the elevation, we know the pressure, and we know the diameter of the pipe there, and we know the discharge, so we know the velocity. At 0.2, we picked that point because that's where we want to know information. We want to know the pressure there. Fortunately, we also know the elevation there, and because we know the discharge and the diameter, we know the velocity there. So I'll give you a few seconds to catch up, and then we're just going to go into the next slide and start to calculate everything. So obviously, if we're looking at this system, what we're saying is when you start mumbling this in your sleep, you'll know you have understood it and completely put it into long-term memory. Right? So you're saying the total energy of 1 is equal to the total energy of 2. And I'm going to just draw while you're writing that. Here is our system. And basically, the energy grade line is a horizontal line above this system. And we know we have V1 squared over 2G, and we're going to have at location 2, V2 squared over 2G, which I'm showing is a smaller distance because you have a larger diameter going to 2. Larger diameter, lower velocity. That's what continuity would say. And if this is Z1, then the distance, when you subtract from V squared over 2G from the EGL, this is the HGL. And so through the transition, the HGL is actually increasing. And the difference from the HGL to the elevation is the pressure. And so we have 0.2. And again, the distance between the elevation and the hydraulic grade line is pressure at P2 over gamma. So concisely, that's what's happening here. And what we would like to do is start to knock these out. If you look at the left-hand side, the velocity we should be able to get from continuity. Same for velocity on the right-hand side. The pressure at 1 was given, 60 PSI. We just need to convert it into a pressure head, P1 over gamma. Z1 was given. So the left-hand side is just some number. So knocking these out. From continuity, velocity at 1 is the total discharge over A1, which is 14 cubic foot per second divided by pi over 4 times the diameter squared, 15 inches over 12 inches per foot squared. And that would give us a velocity of 11.41 foot per second. 11.4 is fine, as I've said before in here, 3-place accuracy is fine. And similarly for V2, we're just going to take continuity, discharge is equal to velocity times area, and rearrange that. So again, this is our 14 cubic foot per second divided by pi over 4 times the diameter squared. We have 24-inch diameter, which I think you know is 2 feet. And that gives us 4.46 foot per second. So again, we understood qualitatively that because we're going through an expansion, we would expect the velocity to decrease. And that is in fact what we just quantified. The next thing we can do is take this energy equation, if you will. And for the energy equation, this is what we're doing. We want to solve for P2. So all I'm doing is bringing the velocity head term and the elevation head term from the right-hand side over to the left-hand side. So what you have is V1 squared minus V2 squared over 2J plus P1 over gamma plus Z1 minus Z2. Okay, so that's just taking the energy equation, B1 is equal to B2, and putting the variable of interest to us, P2, on the left-hand side. And we'll solve it for P2 over gamma and then P2, which is what it originally asked for. I'm just waiting for you to catch up. And of course, I can't see people feverishly writing online, but if anybody wants me to back up, all you have to do is write that into the chat box and the TAs will let me know. So we have, just writing the equation I just developed, P2 over gamma is equal to V1 squared minus V2 squared over 2G plus P1 over gamma plus Z1 minus V2. So P2 over gamma is equal to V1, we just calculated was 11.41 foot per second squared, minus V2 squared over 2G, we just calculated that to be 4.46 foot per second. Notice how after every number I put its dimensions.
Someone wants you to go back to the last slide.
Anything in particular they want to see on the last slide? I just rewrote the equation on the bottom of the slide, so. Okay, so that's divided by 2 times the acceleration due to gravity, 32.2 foot per second squared, plus P1 over gamma. P1 is 60 pounds per square inch, PSI. Everything in the equation we want in BGS, foot, seconds, and pounds. So we'll multiply this by 144 inches squared per foot squared. And that would be the pressure in pounds per square foot. We're dividing by the specific weight of oil, of course. And so that's the specific gravity of oil, 0.83, times the specific weight of water. Temperature was not specified. So again, my guidance to you is assume room temperature while you're in this course. When you leave here, you would have to use the temperature of whatever system you're trying to model. If it's a pipe in the ground, it might be the average ground temperature at that location. If it was for some type of a process in a building, it could be a really hot temperature or cold temperature. That's part of your design. So from the back of your book, at room temperature, the specific weight of water is 62.4 pounds per cubic foot. And then the last two terms, Z1 was 108, and I'm just going to say feet. It is feet mean sea level, MSL. And then Z2 was 128 feet. And that's also mean sea level. So when we calculate all of those, I'll give you some interim result. The first term gives us 1.71 feet. The second term gives us 166.8 feet. And the third term gives us the 108 minus the 128 is minus 20 feet. And, you know, again, what I've stressed to you before, very, very often in pressure distribution systems for liquids, we hold most of our pressure, most of our energy as pressure. And that's fundamentally because energy losses are proportional to the velocity squared. So when we calculate this, this is equal to 148.5 feet. And remember, that's P2 over gamma. So then we can just say that P2 is the specific weight of oil times 148.5 feet. And that again, the specific weight of oil is the specific gravity of the oil, 0.83, times the specific weight of water, 62.4 pounds per cubic foot, times again, what we just found out to be P2 over gamma, 148.5 feet. And that would give you 53.4, take this entire expression and divide it by 144 inches squared per foot squared, because the answer I'm giving you is in pounds per square inch. All right. I just want to ask a thought question. You don't have to answer me. If you had just used fluid statics, would you get the same pressure, a higher pressure, or a lower? I just want you to think about what happened. We went from a location which had a smaller diameter and a lower elevation to a higher elevation where we had a higher elevation and a lower velocity. So in part, by going with a lower velocity, what happened was we took velocity head and put it into elevation or pressure. At the same time, we were increasing elevation. And that comes at the expense of either philosophically, velocity or pressure. Continuity dictates it couldn't have come from velocity. Continuity is dictating the relationship between total discharge and each of the velocities. So when you are changing elevation, it's always at the expense of pressure. So I'm just going to give you this answer. You can try to calculate it yourself. From statics, you would have said that P2 is 52.8 psi. Why is it lower? Because again, you actually took some energy from velocity head and put it into pressure. And again, it doesn't seem like a lot here, and it's not. But in general, you have to understand that once you have fluids moving around, fluid statics is not operative anymore. It's a subset of the general case of where you have fluids in motion. And one last thing I want to do with this, I'm going to give you 5 seconds to catch up. I'm going to move on. And remember, I always save these slides for you. So you'll have these, of course, when the lecture is over. So this is where we started with this problem. The EGL at 1 is equal to EGL at 2. And V1 is equal to V1 squared over 2G plus P1 over gamma plus Z1. And we just calculated all of those terms on the previous slide. Maybe not individually, but we calculated them. So V1 is the 11.4 foot per second squared. P1 was the 60 PSI and Z1 was the 108 feet. And at 0.1, this turns out to be, and this is way too much accuracy, but just to show you, 276.84 feet. And now at 0.2, the velocity we knew from before, that velocity was 4.46 foot per second. The pressure we just calculated, that was the 53.4 pounds per square inch, and Z2 was given 128 feet. This is actually a great check on your work. They should be the same within numerical noise. You know, if you're rounding, you're of course always going to have a little bit of numerical noise. But when you go through a problem, on a test, you may not always have the time to do a check, but on your homework problems, there's no reason why you can't do this. If it doesn't come out, you made a mistake somewhere. Why? Because fundamentally, that's where you started. So at the end, the numbers have to bear that out. And it's not uncommon where we do simple little mistakes. I'm going to go back one slide. We do simple little mistakes like we forget to use the specific weight of the fluid we're interested on one side of the equation and not the other. Or we forget maybe what the conversion is, or we take this term here and we say it's V1 minus V2 squared over 2G, which it's not. Okay? But again, there are very simple mistakes you can make, but there's a very easy way to always check your work with energy. Okay. That gets us to mechanical energy. And we started talking about this last time. And so when we talk about mechanical energy, we're talking about a machine. And the machine is either going to put energy into our systems, that's a pump, or the machine is going to take energy out of these systems. And you would think that these are very mature industries, and they are, but the difference nowadays is we're trying to make much more efficient types of machines with more sustainable components or less expensive components. We want to have an impact on the environment that shows almost negligible footprint. So the industry is always going to continue to improve and change, and then layer over that our ability to remotely control these systems. So nowadays you can control entire distribution systems with your phone, which is kind of amazing when you think about it. And the downside of that is, think of somebody hacking these systems. It's pretty easy to do. And so when you look at the vulnerability of systems, some of it is in the AI that we're allowing to start control of these systems. AI doesn't have the ability to think of the real context of a problem. AI looks at everything as black and white and makes decisions. So always be aware of that, because your generation is the one that's using more and more remotely operated, monitored, and challenged systems. So for each machine, always remember this. Let's say here's a pipe, and we have either a pump or a turbine in it. I stressed this last time. In that setting, inflow is always equal to outflow. Always. When you do install a machine or turn a machine on and off, the entire system performance may change, and I'll explain that a little bit. However, in the new scenario with the machine, the inflow to the machine is always equal to the outflow to the machine. So I think I have a blank slide next. I do not, so let's do it here. Have you ever seen this system before? Big reservoir, hole in the side, water issuing out of it. Yes, we did this last slide, and that's where we did this last lecture. I reminded you of it at the beginning of this lecture, and if you recall, that gave us that tortellini equation. Right? So there is how we would calculate this. And H, again, is the distance from the free surface down to the center line of the free jet. So let's say, same system, only we're going to put a pump here. Normally you do the opposite, you put a turbine there and take out energy, but I just want to show you what happens. So here's the end of the pipe here, and you have a free jet flowing. So again, backing up to the system up above. What a pump does is it takes the energy grade line incoming and it kicks it up some distance, EP. That's the energy that the pump is putting into the fluid. And so the energy after the pump is higher than the energy before the pump. B1 plus EP is equal to B2. If you think about now the system that we were just talking about on the bottom right of this slide, here is the energy grade line going into the pump. We talked about this last time. That free surface is the energy grade line. Free surface for a large reservoir, groundwater table is the energy grade line. And what the pump is going to do is kick it up some amount EP. So when you do the energy analysis here, look at the system without the pump and with the pump. You can see that there is more total energy to be converted into velocity head with the pump. And so the discharge in this scenario is less than the discharge in the right-hand side scenario. So by turning on that pump, you got more discharge. But again, the flow going into the pump and out of the pump is the same. It's the discharge of the new scenario, okay? So I've kind of beat this over the head with a stick, and there will still be a number of you who will tell me that on your homework problems, you've got a different flow going into the pump than coming out of the pump. And as I said, if you find a machine like that, please bring it to me. So for a pump, what we say is that the total energy upstream, oops, how'd that happen? So if the flow is this way, here's the pump. If we have some point upstream, we'll call 1, the total energy upstream is less than the total energy downstream. So again, looking at the pump from the pump point of reference, point 1 is upstream, point 2 is downstream. And again, the energy grade line might do something like this. And remember, the energy grade line can be below the pipe. If you've ever seen a pump, so here's a lake or a cistern, and here's a pump up here, and here's your intake pipe. And then you're going to pump the water, say, to irrigate fields or an orchard or whatever. Here, the energy grade line before the pump is physically below the intake pipe to the pump. So the energy grade line can be anywhere in the system. The only critical thing about when you have the energy grade line, and particularly the hydraulic grade line below the pipe, is making sure that you don't cross that vapor pressure line and start boiling the fluid at ambient temperatures because you lowered the pressure so much. And that's particularly a problem on the intake side of a pump. That's where you can get cavitation because you may have designed the system perfectly, or you're looking at a pumping installation and it's having cavitation problems. You look at the original design and the design was fine, but in the 40 years since they built the system, the pipe corroded. it's got more frictional resistance. And so as the flow goes through it, it just doesn't have as much energy by the time the fluid gets right to the pump. So there are a lot of reasons for this, and it's not always intentional that you design a system to fail, but it could certainly happen over time. So without the pump, we know that the total energies upstream and downstream are the same because you don't have the pump. The pump could be sitting there, and again, we don't have any energy losses in this class yet. And with the pump just sitting there, not being turned on, two energies upstream and downstream are the same. Once you turn the pump on, or once you install the pump, again, what the pump does is put energy into the system. And the only way we can equate upstream and downstream energies with reference to the pump is that we add the energy of the pump to the upstream energy grid line. So EP is the energy the pump puts into the fluid. It's known as the pump head. And in the advanced course next spring, we talk about how to actually size pumps and select pumps for the specific performance you want. And that's about a week and a half of lectures. So it's not a trivial thing. In here, we're just, introducing it. The other thing I introduced last time was power. So if we take that pump head, EP, multiply it by the specific weight of the fluid and times the discharge going through the pump, we get the dimensions of power, foot-pounds per second. And typically in BGS, we don't relate or refer to a pump in terms of foot-pounds per second. We typically refer to it as power, as horsepower. So the conversion factor from foot-pounds per second to horsepower is 550 foot-pounds per second to horsepower. And you'll see that that 550 is what goes in the denominator. In SI, with the discharge in cubic meters per second, specific weight in Newton per meter cubed, and EP in meters, what you get is Newton meter per second, which is known as a what? A watt? A watt. Newton meter per second is a watt. So the conversion factor is typically 1,000 watts per kilowatt. And those of you who are paying your electric bill know that you pay the electric bill on kilowatt hours. So you have an instantaneous rate of use, and then what that meter does is aggregate it. And just like water demand over time has a diurnal curve, electric use does too. In the domestic sense, say in your house, at a water treatment plant, you want that to be almost constant. You want almost everything in the water and the wastewater treatment plant to be constant because you don't want to have to vary a lot of things. Chemistry is pretty important, and chemistry changes when things vary. And so what we do is we produce or we treat things on an almost uniform basis, even though the demand can be incredibly variable. So this power is known as the fluid power. When we just take this equation and we're looking at, again, we're just talking about pumps now. EP is the energy the pump puts into the fluid, Q is what's flowing through the pump, and the specific weight of the fluid moving through the pump is gamma. When we just take those fluid flow variables and develop the power from it, this is known as the fluid power. That's actually what's happening in the fluid. As you can imagine, we need energy to drive the pump. That energy could be coal-fired or wood-fired steam engine. It could be pulleys. Typically, it's just electricity. And what you can obviously imagine is that the energy we put into the pump is less than the energy we can put into the fluid due to either electrical or mechanical inefficiency of the pump itself or the impeller design, which we'll talk about much later in this course when we talk about momentum. So when you think about that the fluid power is not the same as the input power to the pump. If we look at that ratio, the power that's actually put into the fluid versus the power we put into the pump, that's known as the pump efficiency. That little n is the Greek letter eta. So eta P is the pump efficiency. And in the colloquial sense for water or what wastewater, we call that the wire to water efficiency. And again, what it's trying to convey is it's all of the inefficiencies from the electric current that goes into the motor that's spinning the pump all the way to where the energy is put into the fluid itself. And so if we put that into an equation, the pump efficiency is the output or the fluid power divided by the input power, the power we actually put into the pump. And therefore, the input power to the pump is the fluid power divided by the pump efficiency. So when we calculate the fluid power up here, the input power is going to be equal to the fluid power over the conversion factor times the pump efficiency, eta P. And that's the equation on the bottom. So in the remaining time, I just want to do a very simple example. So what we're going to have is something we've been drawing a lot of today. We're going to have 10 gallons per minute. In this case of water flowing. We're going to have a pipe and the pipe diameter is 4 inches before and after the pump. We're going to have a gauge before the pump, and it's really common to have gauges on both sides of a pump. In this case, we only have one. And the gauge before the pump is saying that we have 10 pounds per square inch. And there's two pieces to this problem. The first one is, what is the increase in pressure when the pump puts 0.5 horsepower into the fluid? Okay, so basically, we're going to call point 1 where we have that gauge because we know information there. We not only know the pressure, but because we know the diameter and the discharge, we know the velocity. And downstream, we're just going to call point 2 somewhere downstream of the pump, very close to it, because we want to know the pressure there. Specifically, we want to know the pressure difference. So point 1 to point 2, we want to know P2 minus P1. That's what it's really asking. And we can find P2 once we know the pressure difference. So the second thing we're going to ask in this question is, what's the input power to the pump? PN or PI, if the pump is 87% efficient. Very, very commonly for the types of pumps we use in civil engineering applications, typically for water or wastewater, pump efficiency is 85 to 95%. It's very high because, again, it's a very mature field. There are a number of instances where we would operate pumps at much, much less efficiencies. For example, the fluids lab. We operate at pathetic efficiencies, but that's for demonstration purposes. We should actually have 3 pumps for the types of labs we're running, but what we did was just get one big pump that we could operate over an incredible range. And so it's not uncommon that for a lot of the labs, you're actually working at maybe 40% efficiency. Pumping concrete. might have a very inefficient pump. So again, there are applications where that it is what it is, and we just have to deal with it. So with this scenario, I'm going to write this on the next page, but what we're saying is B1 plus EP is equal to B2. And from that, we're going to get P2. How? Well, you know that B1, and again, I'm going to write this on the next page, on the next slide, is V1 squared over 2G plus P2 over gamma plus Z2 plus EP is equal to V2 squared over 2G plus P2 over gamma plus Z2. So the first thing I see is Z. And what we're going to do is say Z is equal to 0 on the pipe center line. It's a horizontal pipe. Point 1 and 2 are on the pipe center line. And so Z1 is going to be equal to Z2, and they're going to just cancel out. I think you can see that V1 and V2 we can get from continuity. You have 10 GPM downstream of the pump, you have 10 GPM upstream of the pump.
We have a question about why there's 2 on both sides of the equation, like it's P2 on the.
I'm sorry,
right and left
that's a
side.
screw up, that's why. That should be 1.
And for Z as well,
And what?
Z as well.
Yeah,
Yeah.
yeah, that was multitasking, writing and talking at the same time. So they all should come from this. Nowadays, I'm condemned by these slides because I post them for you. Before, I would put them on the board and erase them, and there was no documentation. All right, so again, I said I would write this again, and this time I'll write it correctly. So now what we have to do is start to knock things out or identify what you know. We already said that that's true. That's continuity. Can you tell me a story about A1 and A2? They're the same. So what does that say about V1 and V2? So can we just say the first law of calculus, when in doubt, cancel out? Sure. So we'll get rid of those 2 terms. That makes life a little easy. And now what we also know is that Z1 is equal to Z2 is equal to 0 because we intentionally put Z right at the center line. Could we have put Z 10 meters below or 20 feet above? Absolutely. But Z1 and Z2 are still the same. So what this leaves us with is P1 over gamma plus EP is equal to P2 over gamma. And obviously we're after P2 minus P1, so we can solve this equation for P2 minus P1. Okay. And again, if I just bring gamma to the other side of the equation, that gives us what the question was asking. What's the pressure difference? So what hasn't jumped out at us, we know P1, we know gamma is the specific weight of water. We're after P2, but we don't have EP right now. However, we were given some information, and that was that the fluid power is equal to 0.5 horsepower. And we know that the fluid power is Q gamma EP divided by the conversion factor from foot-pounds per second to horsepower. And so what we do recognize from this equation is we know the discharge, we know the specific weight, we know the conversion factor. So all we need to do is rearrange this equation to get the pump energy. Before I do that, the discharge was 10 GPM. And remember, there's 448.8 GPM per CFS. So that 10 gallons per minute is 0.022 cubic feet per second. Those of you who have a well for your household water supply, it's not uncommon that those houses would have a 5 say 10 to 12 gallon per minute pump. That's really common. We typically use water. For example, our fixtures might be yielding anywhere from 2, maybe close to 8 gallons per minute. And so what typically happens is we'll have a storage tank. It's either pressure or atmospheric tank in the house. When we turn on the faucet at a really high rate, first the water comes from that storage tank, and then there's a pressure switch on it. And once it hits a certain level, the pump kicks on and starts refilling it. That's not only how your house works, that's how all these distribution systems work. It's no different. So we have the discharge, and we're just going to rearrange that equation and say that the pump energy, EP, is going to be equal to the fluid power, we're just bringing everything to the other side of the equation, times the conversion factor divided by Q gamma. So again, all we did was take this equation and rearrange it by isolating EP. That's what we were after. So the fluid power is 0.5 horsepower. The conversion factor is 550 foot-pounds per second per horsepower. So that gives us foot-pounds per second in the numerator. And then in the denominator, we have the discharge of 0.022 cubic foot per second, and the specific weight of water is 62.4 pound per cubic foot. And that gives us a pump energy or pump head of 198 feet. So we're putting we're putting a half horsepower into the fluid. That sounds like a number typically people might use as a frame of reference. But really, the same way of saying that is we're putting 198 feet of energy into the fluid. That starts to become abstract. So now that we know that, what we're going to do is put that into the equation that we just generated. I'm going to write that on the next page. So again, what we had was P2 minus P1 over gamma is equal to EP. And we just calculated that EP is 198 feet. So in this case, P2 minus P1 is equal to gamma EP, which is 62.4 pound per cubic foot times 198. And that will give us an answer in pounds per square foot, 12,340 PSF. And if we divide that by 144 inches squared per foot squared, that's 85.7 PSI. That's the pressure difference. P2 is equal to P1 plus that pressure difference. So that's 10 PSI plus the 85.7 PSI. So that's 95.7 PSI. I have 1 minute remaining. And that was that if the pump energy is 87%, what was the input power? And remember, the pump efficiency is the fluid power, which is Q gamma EP, divided by the input power. And so from that, we can calculate that the input power is the pump fluid power divided by the efficiency. And the problem statement said that we're putting 0.5 horsepower into the fluid. The efficiency is 87% or 0.87. So what we're putting into the pump is 0.57 horsepower. And what the pump delivers to the fluid is 0.5 horsepower. Wow, I know I'm a few seconds over. It's a Friday. You want to get out of here. Are there any questions? Chat room. See you in 3.5 hours, maybe. You have a meeting in half an hour?
No, I said you haven't been saying in your meeting
I haven't.
in the last 5 minutes.
I've lost my game.
Yeah.